Hello all, I hope you are having an amazing day wherever you may be. In today's video, we will be going over Kirchhoff's current law and Kirchhoff's voltage law, or KCL and KVL for short. So I already have the definitions written down here. So KCL basically is all the currents entering a node are equal to the currents leaving the node. So if you remember from my previous video, we talked about branches, nodes, and loops. So these are what the laws are referring to at this point. So all the currents entering a node are equal to the currents leaving a node. And for Kirchhoff's voltage law, it is the sum of all the voltage drops around a loop is equal to 0. So if you forget what branches, nodes, or loops are, you can go back and refer to the previous video, or you can look it up in a textbook. But I will show you how KCL and KVL work in action right now. And so we have a small example here of a circuit. So we can see from the instructions that we want to find the voltage drop across each resistor and also the current in the circuit. And so I have each resistor labeled as R1, R2, R3, and R4 respectively with a 12-volt voltage source input. And as we can see on the side here, I have all of the resistor values labeled here. And first things first, in order to apply KCL and KVL, what we need to do is go ahead and apply another rule that we learned in a previous video, which is called series and parallel, okay? But before we get to that, let's go ahead and label each resistor with a voltage. So I'll go ahead and say plus or minus VR1, plus or minus VR2, and we will go ahead and say plus or minus VR3, 4. And the reason why I'm going to go ahead and make this a plus or minus VR3, 4 at the end here instead of also putting one for R3 is because in parallel, the voltage is actually the same across those resistors. And another rule is that the current is the same for resistors in series, okay? So this is very important. So whenever we go to apply these resistors in parallel and work that out, we will see we only need to find one current because all the resistors will be in series, so that means that the current is the same throughout the whole circuit. So we will go ahead and put resistors R3 and R4 combined. And if we remember from last time, these two resistors would be in parallel. And so if we remember, the parallel equation for resistors is simply R3 times R4 over R3 plus R4, which is equal to, let's see, we have 6 times 12 over 6 plus 12. So if we do some math, that means we have 72 on top and we have 18 on bottom, which should give us 4 ohms. Okay, and we can go ahead and redraw our circuit here, which I will go ahead and do. So this voltage source will still stay the same at 12 volts, and our two resistors on top, R1 and R2, will also stay the same because we haven't done anything with those. And we will have just one resistor on the side now because we combine resistors 3 and 4 into 1. So now we will go ahead and call this R34, and R34 has a new value, which is what we just calculated here, which is the 4 ohms. So now we can say this is 4 ohms, and we still have this voltage drop here, which we can say is VR34, okay? And we still have resistors R1 and R2 here, along with the voltage drops. And now we can go ahead and apply our loop. So we only have one loop in the circuit, and I'll go ahead and draw that in, L1. And so we can say loop 1. Now, people can write Kirchhoff's voltage law in a couple different ways personally, I always start with the sign that you hit. So for example, we'll be going up through here like so. So we see the negative is first for the 12, so we'll go ahead and write negative 12 because that is the voltage. And as we're passing through to the next resistor here, we can see that the plus is first. So what we can say is plus I R1. And the reason why we say the plus is because we hit the plus first, and you may be wondering why I put IR1 instead of the VR1 here. Well, that's because Ohm's law is V equals IR. So I'm essentially just putting the equivalent of the voltage of resistor 1 here in Ohm's law form, which is the current times the resistor 1. And so we can go ahead and do the same for resistor 2, which will be IR2. And then we can also do the same for the new resistor we made from putting R3 and R4 in parallel, which is now R34. And those will be equal to 0. And now we can go ahead and find the current of this circuit by using some common algebra here. So we can go ahead and take the I out of R1, R2, and R34, and we can move the 12 to the other side. So this will end up looking like R1 plus R2 plus R34 is equal to 12. Okay. And now for the next step, we can go ahead and rearrange this equation to solve for the current throughout the whole circuit. Because remember that with KCL and KVL, the current is the same for resistors in series, and voltage is the same for resistors in parallel. And so since we have this whole circuit, all resistors are in series here, so that means that we only have one current. So if we rearrange this equation as 12 over R1 plus R2 plus R34, we can go ahead and plug in those numbers. So we will get 12 over 6 plus 2 plus 4, which will give us 12 over 12, which is simply 1 amp. And now we know that the current throughout the whole circuit is 1 amp. And now, since we know the current throughout the whole circuit, we can now find the voltage drop across each resistor. So going up here to VR1, we can now find it by VR1 is equal to the current times R1, which is simply 1 amp as we calculated from here. And the resistance value of R1 is 6 ohms. And I got that from right here, where we already listed the value. And so 1 times 6, that is simply 6 volts. And that will be our voltage drop across resistor 1. And same thing for the second resistor. We can say VR2 is equal to the current times the value of the second resistor, which will once again be 1 amp, because as we said, the current for the whole circuit is 1 amp. And then we want to multiply that by the value of the second resistor, which is 2 ohms. And then 1 times 2 is simply 2 volts. And now for the final one, we can say that VR34 is equal to the current times R34. And we can find that we have 1 amp times 4 ohms, which I'm getting right here, which is what we calculated from this parallel equation right here. 4 ohms is equal to 4 volts. Okay. And now, it says in the instructions up here that we want to find the voltage drop across VR3 and VR4. And as I stated before, and I will state again because this is very important to know, that the voltage for resistors in parallel is the same. So we can easily say that VR3 is equal to VR4 is equal to VR34, okay? Which is all equal to 4 volts. Now you may be wondering, well, how can I check to know if these values are right for the voltage drops? Well, let's go ahead and look at the circuit here. We know that the input voltage of the circuit, the voltage source, is 12 volts, okay? And our ground is the bottom node here, okay? And to go ahead and reference this as the ground, we can go ahead and put a small triangle here, which means ground. And now, since we calculated the voltage drop across all of these resistors, this means that if we were to add each resistor and then subtract it from the input voltage, this should equal 0, which is ground, which means that we have solved the circuit correctly. So let's go ahead and do that. So we have our values, so we can go ahead and say 12 minus VR1 minus VR2 minus VR34 is equal to 12 minus 6 minus 2 minus 4, which is equal to 12 minus 12, which is 0. So we can see that this is 0 volts, which means that this is indeed ground. And GND just means ground for short. So this is an introduction to KCL and KVL, where we applied some other rules that we know already, such as branches, nodes, and loops, and also resistors in parallel and resistors in series. So basically, just practice, practice, practice. This will help you get better. And this is a relatively simple circuit, but if you need more practice, it's always good to start with circuits with just one loop, and then you can build yourself up to more complicated loops to where, circuits where there's more loops and all that stuff. I hope this video is able to help you, and I hope you have a great rest of your day, and I'll see you in the next video.